Hi, everyone. Thank you for coming today. This is Ammar Hattab. Today I want to present my work of linear arrangement of spherical markers for absolute position tracking of a passive stylus. So basically, we want to use the spherical markers attached to the back of a stylus to track the tip of that stylus. So this has many applications for general measurement, for reverse engineering. For example, when you have a physical part and you want to detect the surfaces of this part digitally, have a digital CAD model of that part. For 3D modeling, for example, in virtual reality applications, for digital writing, for medical applications like in surgery simulations and other medical applications, and general for many other applications. So in our opinion, the current methods to do that are complicated or limited. For example, the industry standard is to use a coordinate measuring machine, CMM, which uses a mechanical arm to track the position of a stylus tip. These devices are expensive and limited in space because we need to be they need to be physically attached to the stylus all the time. On the other hand, optical devices for position tracking are portable, but they are also bulky and cumbersome to use because they need also to be facing one direction toward the camera all the time. So to solve that, we suggest a new way to do that, which is to arrange the spherical markers along a line, 2 or more markers, and use them to detect or to find the tip location of that stylus. So this provides like a simple, compact and lightweight, easy to hold stylus or tool in general. And also this tool is symmetric along its axis, so it doesn't need to be facing the camera from one direction all the time. As for previous papers, there are some papers that use some patterns and attach them to the back of the stylus or the tip of the stylus. But the problem here is that we need to be, or the stylus need to be closer to the camera to compare to our work to be able to recognize these patterns. Also, some other papers use non-spherical markers like cylindrical markers or point LED light markers. But these also provide limited directions for the stylus compared to the spherical markers. For some other papers, as I said, some of them used a nonlinear arrangement of spherical markers, which as we said, are more bulky and not compact. So for the system setup, we have the stylus and the spherical markers. And here's the object that we're trying to measure, for example. And we have the stereo camera. At the same time, we have a light source. So the markers, they could be retroreflective markers that needs a light source. They could be active light markers on a spherical shape. So in our setup, we have retroreflective markers that needs a light source from the camera side. For the tracking algorithm, we start by capturing stereo images of the markers or for the tool, but the important part are the markers. They need to be like appearing in the camera all the time. Then we rectify these stereo images using the calibrated stereo cameras. Then we apply some thresholding algorithm to detect the regions of these markers. We also apply some edge detector, like in this example, a canny edge detector on the 2 images. And we only mask the edges using the thresholded image. So for the remaining edges, we fit ellipses to them. And for these ellipses, we match them between the 2 images. And then we triangulate the center of these ellipses to get 3 points in 3D representing the 2 markers. And at the end, we just need to extend a line between these two, the center of the two markers, to find the tip of the stylus along a pre-calibrated distance. So this pre-calibrated distance could be like measured at the manufacturing time, or it could be computed by some optical algorithm. For example, we could move the markers, move the stylus while keeping the tip at one point, and capture images between all these orientations, and then find the intersection point between all of the orientations of the markers to take this recalibrated distance. Now, to evaluate the system, we need to find the range of distances and orientations where we can get an accurate tracking. To measure the accuracy across these ranges, we could replace the stylus tip with a third spherical marker. We can see it here on the right. And then we apply the same algorithm on the captured images of this stylus. And we compute the orthogonal distance from the third marker to the line connecting the two markers or the base markers. So this distance, this orthogonal distance, indicates the accuracy of the system, both optically and mechanically. Optically, in terms of how accurate the stereo camera system, and mechanically in terms of how straight the stylus is in the time of manufacturing. So in all our experiments that I will show later, we use a synchronized USB video camera module, like that costs around $80, with a baseline of 7 centimeters and a focal length of 1.135 millimeters. At the beginning, we measured the accuracy along distances, like we moved the stylus away from the camera, and we captured many images while we doing that. And the result here, we noticed that between 20 centimeters and 80 centimeters, the accuracy is less than 1 millimeter, which is good for many applications. Now, this range could be also enhanced if we upgraded the camera or replaced the camera, the stereo camera. For example, we could increase the baseline distance to enhance this range. We could also increase the focal length of the lenses or enhance the pixel size of the camera. So we could, in general, we could upgrade the camera to get more accurate system, or an accurate system along a larger, longer range. We also measured the accuracy along different kind of rotations of the stylus pen. For tilting rotation, which is the rotation in a plane orthogonal to the stereo camera plane, as we can see in the picture, we found that on angles less than 15 degrees or more than 160 degrees, the markers start to cover each other. So the ellipses in the captured images start to merge, and so it's hard to distinguish between them. So the algorithm fails. So we have two blind spots using this method in the sphere of orientations, as we can see in this picture. One to the front and one at the end of this sphere. For other type of rotations, for example, for rotation in a plane parallel to the stereo camera plane, or for rotations around the axis of rotation of the stylus pen, we found that there's no significant difference in accuracy, which is expected. So in summary, we proposed a new method to track the tip of the stylus, and we found that it's accurate across a wider range of distances and rotations compared to previous methods. Thank you. Yeah, I can get any questions now.